Okay, in this talk I'm going to be talking about my paper entitled An Accumulative Model for Quantum Theories. It's published in the most recent version of Electronic Journal of Theoretical Physics, open access. I also have a YouTube presentation, and here's my address, my email. If you're interested, I would love to follow up with a seminar at your university. Now, this investigation was motivated by something everybody knows. Quantum mechanics is strange, has many properties that are paradoxical and different to understand. And could it possibly be that the reason that quantum mechanics is so paradoxical is that we're simply looking at it from the wrong perspective, from a wrong paradigm? So I'm going to ask some questions. Whether or not you agree with my model, hopefully these questions will get you thinking. So first question, does time have to be the basic dynamical variable? We always think of equations, physical equations, as evolving in time. And things seem to think of the past events causing present and future events. Now, could our preference actually be due to our observational bias? Think of the geocentric view of the universe, for instance. People always thought that the Earth was still because it seemed like it was still from their perspective. Now, the fact that time seems to be the causal variable, could this just simply be due to our perspective? Well, you might want to ask, why even ask this question? What's the point? Well, the point is that quantum mechanics, based on this sort of time causality, seems to have a lot of paradoxes. And in fact, quantum mechanics does not allow for strict causality. So maybe there's something wrong with our whole viewpoint of causality, and we need to rethink quantum mechanics from another angle. Okay. All right, so consider this other fact. I'm sure other people have noticed this. But the question is space-time a process or an outcome? Now, think of a hanging cable. You take a cable and you suspend it between 2 points, and the cable will settle down into the configuration that gives it the smallest potential energy. So we have a minimization principle that comes from a process, and that leads to a minimum configuration. Now, consider the principle of least action, fundamental principle of mechanics. If you have a particle at a space-time point moving to another space-time point, you fix the two endpoints. And the path it takes in between minimizes the action. So could this minimization principle also be an outcome of a process rather than exemplifying a process itself? So in analogy to what I've said about the hanging cable. Okay, now let's go a little further with that. If the principle of least action is indeed an outcome, then what kind of process could produce it? Well, it can't be a process in time, because time is part of the configuration that's determined by the process. So there must be some additional dynamical variable, which I call the A dimension. So I augment the space-time that we see by an additional dimension, which I call the A dimension. And the process by which the universe develops its configuration is a process that occurs in the A dimension. So I think of the way I think of it as a pre-universe that changes its configuration until it reaches a certain point and develops to the point where it becomes the universe that we see. Okay. Now, I compared least action with a hanging cable. Least action derives from path integrals. I mean, if you think about it, least action comes from the principle of stationary phase, and the principle of stationary phase comes from path integrals. So path integrals underlying this idea of least action. Now, if you think about a path integral, it's the sum, or usually physicists do an integral, but I simulate, so I say summation. The summation over all paths belonging to a certain state of e to the I times the action of those paths. And this is proportional to the wave function for the state U. You can read Feynman's Nobel lecture. He gives an amusing account of how he came across this realization. But you can see that this quantity kind of suggests an accumulative process, because it is a summation after all. Now, let me introduce to you a process that I became familiar with when I was working for Motorola. When you have a cell phone, in order to locate the base station that it talks with, it undergoes an accumulative process. It looks for certain signatures, and as you move around, it accumulates a signal. And when the signal reaches a certain threshold, then there's a detection, and the cell phone is located and registered by the base station. So I'm proposing that the universe comes into existence in an analogous way, that there's a so-called pre-universe that moves through configuration space. As it moves through configuration space, it has some kind of oscillatory amplitude. This oscillatory amplitude grows until it reaches a threshold. Once it reaches the threshold, then the observable state of the observable universe is realized. And I'll show you a picture in a moment. Now, this model actually explains all quantum paradoxes. And the reason it explains all quantum paradoxes, it explains path integrals. And all of quantum mechanics can be expressed as a mathematical consequence of path integrals. For instance, I show here the Born rule actually comes out of this kind of signal processing calculation, that the probability of the location of your, for instance, when your cell phone, the probability of location of your cell phone is proportional to the squared amplitude of the signal at that location. So the Born rule just pops out. All this complicated vacuum structure, for instance, there's no complicated vacuum structure. That's simply a vestige of the process, the fact that the universe, the pre-universe, is wandering through its configuration space. Okay. Now, the model actually gives physical predictions. Unfortunately, I can't tell you the size of this effect, but the model does predict that there's some flattening out of the wave function, that peaks of the wave function will be slightly reduced, and regions of lower density will actually be enhanced compared to theoretical quantum numbers. Okay. So here's just a picture of the wandering of the pre-universe. This is supposed to show the path space, which gives all the paths for the potential paths of the universe, and U1, U2, U3, etc. These are potential states of the universe. And I'm talking about the entire space-time universe. This process determines the entire space-time universe in one fell swoop. So when I show this trajectory of the pre-universe, really this is a mathematical representation of the fact that the pre-universe is, the configuration of the pre-universe is changing. So I think of that mathematically as the pre-universe wandering through phase space. So as it moves through this phase space, it accumulates an oscillatory amplitude. And it's wandering all through this phase space. It samples everywhere. And then finally, the point where it reaches a certain threshold, where the oscillation reaches a certain threshold, this determines the state of the observable universe. Okay, slightly more complicated picture that's necessary for the mathematics is that I divide the universe up into observable system and non-observable system, but the basic picture is the same. You still have this wandering, and you still have the wandering until the oscillation reaches a certain amplitude, and the state, the observable state, where the pre-universe is located at the point where the oscillation reaches its threshold, becomes the state of the observable universe. Okay, so here's some pictures of the simple simulation that we did. Here's our wave function, very simple wave function. Here's our probability amplitudes associated with that wave function. And here I'm plotting the wave function squared, amplitude squared of the wave function, versus the probability observed in our simulation. So you can see that the amplitudes, squared amplitudes, line up very, very closely with the probabilities. There is some error, and the error is given here. And these different curves correspond to different model parameters. As we increase the threshold, as we increase the accumulation length, the prediction by the model becomes closer and closer to quantum prediction. But you can see always then in all cases that the smaller probability amplitudes are heightened and the larger probability amplitudes are slightly reduced. So this is an effect that we would predict from this model. The size of the effect is not known, just as in the case where with Brownian motion, you can't predict the size of the effect of Brownian motion without knowing the size of molecules. You actually use the Brownian motion to find the size of molecules rather than vice versa. Okay, that's it. Thank you very much.